Okay, so let's imagine another situation. You should be able to still see um, the board down here. I think somewhere it should be right around here if I kind of am remembering where my image goes when I do this. You should be able to see the board from what we just had up there. Let's look at a slightly different setup for the problem. Let's look at a setup where the initial condition we've got, the condition on the x-axis. So here our coordinate axes are x. That's what the horizontal axis is, and the vertical axis is like the u of x of t. So in this image, the vertical axis is not the t-axis. It would be like what's coming out of the board. Okay, the z-axis maybe if you want to think about it that way. At any rate, this is the graph of the initial curve, and we've got 1/2 here on x less than 0. At this point right here, this is now 1, but for x bigger than 1, it's equal to 1. And I have this parameter a here, a equals 1. And what you can see is that I can slide it closer and closer and closer till I get something like that. Okay, I can slide it closer and closer, closer. This is what we start with. This is what we have here. This is the problem. I mean, this is the condition as given in the problem, and then this is kind of getting closer and closer. So what we can do is we can basically think about solving this problem for every parameter value a, and then taking the limit of that as a goes to 0. And then what I'm saying is that the characteristics that we found in the previous problem are just going to be the limiting case of these characteristics. Okay, so what do I mean by that? So here's what I have. Here I have is the same parameter value a set to 1. So I've got these blue characteristics. These are going to be the blue characteristics that we had. They were blue on the board. These should be purple characteristics to make the colors consistent with what we had on the board. Should have done that ahead of time, but didn't realize there was a difference. And these will be the black characteristics, again, to keep consistent with what I have on the board. Okay, so these blue characteristics haven't changed. What's changed is that the purple characteristics, the dashed line, the limiting case, now starts at this parameter value a. And then between 0 and a, we just have a normal u function, and I can just draw the characteristics normal like that. Okay. Now the difference is that it's still going to, like, the x equation is still going to depend on the value of z at these points right here. But again, z is still going to be constant along these characteristics, and there's a ramp up from 1/2 to 1, and whatever the value of u is there is going to be the value of the characteristic. It's going to be the slope. It's going to be 1 over the slope. And so now we can see what happens. As a goes to 0, these characteristics get squeezed, right? And so if you sort of imagine, in theory, solving this problem for every parameter value a, our solution is going to depend on that parameter a. So we'll have u of xt, and all of those formulas are going to depend on a, both the value of the function and like where the demarcations are. Okay, so it won't be for t greater than x, it'll be t greater than whatever this purple line is there. And so that's going to depend on a. And then if we let this parameter value go to 0 in the limit, we get the exact picture. Obviously this is drawn better, but we get the exact image of what we had on the board. Okay, so another way to think about this is sort of thinking about these characteristics as being the limiting case of what's happening as, this. We approximate our discontinuous function with a continuous function, and then take the limit of that, and we get what we had. Now, one thing to point out here is another way to think about this then is we can think about all of these characteristics from 0 to 1. All of these characteristics, all of these initial values for u are all present at 0 simultaneously. Okay, so we have a new thing here. The new feature for this problem is that all of these points, if you look along the x-axis, all of these points have exactly one characteristic emanating from them. But 0 has infinity characteristics emanating from them, just because we're imagining that all of the characteristics, all of these characteristics, all of the values of u from 1/2 to 1 are present at 0 simultaneously. And so we have all of these characteristics existing at once. When we have a case like this, we call this an expansion wave. Okay, and the reason is the following. If you imagine drawing t values here, or just looking at a fixed t value, the distance between the blue and the purple line gets bigger and bigger and bigger. So it's like one of those fans that you can fan yourself with, that you open up, and as you open it up, you have the two little you can't see me. Maybe if you look down now in the video, you'll see, you have a fan that sort of opens up like this, or let's say it's like this, and it opens up like that, right? And so my arms here represent the dashed lines and the characteristics in between. So this is called an expansion wave or a fan wave, and we're going to talk more about that in the next couple of examples when we look at traffic. But this is the bottom line for how to solve problems like this. In the area where there's no characteristics passing through, you imagine there's a characteristic passing through, you figure out, okay, this is going to be where it starts from, this is where it ends. If I have a point on that line, here's what the slope is, and then you're going to use the PDE to figure out what the value of the solution is there. We will, of course, be looking at more examples of this, but I wanted to show you this Desmos graph.